In this video, I'll explain how to install SystemML. We'll walk through a simple Hello World example and a matrix multiplication example. We'll implement three different algorithms to train linear regression model, namely direct solve, batch gradient descent, and conjugate gradient method. We'll invoke the existing SystemML algorithm, in this case linear regression direct solve, using ML context API. And we'll invoke an existing linear regression algorithm using the ML learn API. Finally, we'll look at an example which shows how to use Keras model with SystemML. You can install SystemML using pip. Since I've already installed it, I will just check the pip version, the SystemML version. SystemML 1.0 requires Spark 2.0 plus. So if you're using a different kernel, you can change it with this menu. Here, we import the ML context and DML objects. We create an ML context object by passing Spark context to it. And finally, we check the version of SystemML. In this example, we create a simple DML script that prints Hello World. Instead of using SystemML's built-in function print, let's say we want to use Python's built-in function print. In this case, you would create a string in DML, get it as an output, and then print it. Let's load NumPy and scikit-learn for future examples. Here, we create a random matrix X with 1000 columns and sparsity 0.5. The number of rows is passed by the user through a variable $. Then, we multiply the matrix X with its transpose and compute the sum. We pass the $argument via input method and get the output S via output method. We execute the script using ML context and print the sum. As you can see, it spawned a Spark job likely to generate a random matrix. When the job is finished, you'll see a value for S over here. Now, let's load the diabetes dataset from scikit-learn. We load the dataset, and just to see the content of the dataset, we print a scatter plot. We mark the training data points with black and the test data points with red. The x-axis denotes the features and the y-axis denotes the response. As you can see, the response values are between 0 to 400, and we can double check that by just printing that. Now, our goal is to train a linear regression model, essentially a line that somehow passes in between. So, if a line is drawn this way, the value 0 should correspond roughly to 150. Before we jump to linear regression, let's look at two preliminaries. The built-in function solve computes the least square solution for systems of linear equations, Ax equal to b, for vector x such that the norm Ax minus b is minimized. It is important to know that this function can only operate on small to medium-sized input. For more details, we can look at solve in our language reference. linear regression model assumes that the relationship between features and response is linear. The goal then is to estimate the regression coefficient W. In this example, we'll assume a squared loss. Let's differentiate the squared loss with respect to W, and we get this expression. We set the expression to 0 to find the minimum W, and after rearranging the terms, we get W to be this expression, which can be solved with our solved built-in function by setting A to X transpose X and Y and B to X transpose Y, which you can see here. Because we want to use add a bias, we can append ones to our features. We can pass X and Y via input method and fetch W and bias with output method. Finally, we execute the script and print W. Oh, sorry. Once W is computed, we can use it to print the line that we discussed earlier. As you can see, 0 is roughly 150. Next, we see how to implement linear regression using batch gradient descent. Gradient descent is an extremely simple algorithm. What it says is you can start at any initial point, then you compute the gradient at that point and take a step in the negative direction. So in this case, you see that you might get the gradient in this direction, and you walk in the negative direction, and so on and so forth, until you reach the minima. The exact algorithm is given here. As we discussed earlier, the gradient is given with this expression, and to compute the step size, we can perform a line search. The DML script for gradient descent is given here. We compute the gradient using this expression and the step size with the expression given here. And then we walk in the negative direction. And finally, we print the line learned using batch gradient descent method. So the feature 0 corresponds roughly to response 150. Next, we look at conjugate gradient method. Here, the gradient descent might take steps which are extremely similar in many times. The solution is to enforce conjugacy. So instead of taking many steps to reach the local optima, you can take conjugate or orthogonal steps to reach the minimum. So as you can see, conjugate gradient takes far fewer steps than gradient descent. The exact algorithm is given here. I will not go in detail for the algorithm and refer you to the algorithm from Wikipedia. And as you can see, it found a line which is similar to the earlier ones. Now, you may not want to implement your own algorithm, but use one of the pre-implemented algorithms. The pre-implemented algorithms are available on our GitHub in the scripts folder. So let's say you want to invoke linear regression DS. To invoke linear regression DS, you want to pass X, Y and get as an output B. you can create a script object by using DML from resource, pass it X and Y, and it will execute that script. Let's say if you don't want to use, if you're a scikit-learn user, in which case you simply want to create a linear regression object and then call a fit method and finally a predict method. So for that user, he can simply use our MLlearn API. You create a linear regression object and invoke fit and predict. As you can see, we read down the same line. Next, we see how to use Keras with SystemML. So, the below example is given in more detail here. This page shows that there are 3 different ways to implement a deep learning model in SystemML using a DML-bodied NN library, an experimental Caffe to DML API, and an experimental Keras to DML API. The Caffe to DML API allows a Caffe user to express the model in Caffe's proto format and use it in SystemML. Similarly, Keras to DML API allows a Keras user to implement its deep learning model in Keras. The pros and cons are given in this table. What we are going to do is we are going to train LeNet using MNIST dataset. So what we do is we load the MNIST dataset, split it into train and test, and then create a Keras model, which is given here. It's simply a convolution followed by max pooling, followed by convolution and max pooling, and 2 densely connected layers with a dropout in between. We are using ReLU activation and chain padding for convolution layers. Once we have created a Keras model, we can pass it to Keras to DML and then invoke fit and predict as it is our MLlearn API.